So very good day to everybody present here. Today's class we'll discuss about data structures. In data structures, we'll discuss much more about recursion. You'll discuss more about the recursive tree, and then we'll discuss about the stacks and queues of data structures. I would dedicate this especially for you, my dear students and young researchers. And you can reach me at Professor Dr. Christo Ananth. You can reach me at dr.christoananth@gmail.com. So before beginning the session, let me thank God for giving me this wonderful opportunity to deliver this useful session to share my knowledge among my fellow national, international participants, students and young researchers. So today's class we'll discuss more about different topics. The first topic is all about recursion data structure. Then we would discuss about the base condition in recursion. Then I will give you the difference between the direct as well as indirect recursion. Then of course I will discuss about the difference between the tailed as well as non-tailed recursion. With an example, I would be explaining you a C++ program to demonstrate the working of recursion. And then I'll discuss about the memory stack, about the program and recurrence relation to find the Fibonacci series of n where n greater than 2. So this is a particular C++ program to actually exaggerate or maybe progress the working of this data structures in Fibonacci series using this recursion technique. And then we'll discuss about the recursive tree. We'll discuss about the C++ code to implement factorial. And then we discuss about the factorial recursion. We discuss about the advantages and disadvantages of recursive programming over normal iterative programming. And then we discuss about the stack data structure, about the various application of stack. Then we discuss about the implementing stack using arrays. Finally, we are going to go to the last part of today's session, which is about queue data structure, about the applications of queue data structure, the properties of priority queue, the operations in priority queue, about the types of priority queue, and finally we discuss about how to implement this priority queue. Okay, so at regular intervals I will be discussing you with some independent works. We have already discussed this independent works in the Google Classroom. I hope you would see this in the Google Classroom. And at regular intervals I will be giving you some short videos to explain the knowledge in our topics. So we start up with the recursion data structure. Actually, recursion means it's actually a process in which a function is going to call itself either directly or maybe indirectly. So this is what you call it to be recursion. And the corresponding function, you call it as the recursive function. So using recursive algorithm, you can solve certain problems like for example, tasks of Hanoi, what you call TOH, and then in order or pre-order or post-order tree traversals. And then we discuss about the DFS of graph. Okay, so this recursion, with the case of the recursive tree, we are going to bring about a mathematical interpretation where we would be considering a problem. We have a programmer who's going to determine the sum of the first n natural numbers. Okay, so in order to find the sum of first n natural numbers, we can do it by using any simple approach. Like maybe you can start from numbers from 1 to n and you can add them. So generally you have a function, we have approach 1, you simply add one by one. For example, if you have to find the sum of first n natural numbers, it should be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 up to n. Okay, so you define the function of n to be 1 plus 2 plus 3 plus 4 up to plus n. Okay, and then there is also another mathematical approach. So first approach is you add 1 plus 2 plus 3 up to n. Second approach is you give the f of n is equal to 1. Okay, here n is equal to 1 and f of n is equal to n plus f of n minus 1. Okay, so this is actually n is actually the last number. Okay, the last digit plus f of n minus 1. Okay, so this n is greater than 1. Okay, so it is actually 1 plus f of n minus 1. Okay, so it is maybe, let us take in the case 2. Okay, so the function gets added up. That's a simple difference between approach 1 and approach 2. Because in approach 2, the function f of itself is going to call inside the function. So you call it as a recursion. Okay. And the function containing the recursion, you call it to be the recursive function. At the end, this is actually a tool for the programmers to code some problems, and it is more easier, more efficient as well. Okay, so this is what you call it to be recursion in data structure. So this is the base condition in recursion. In recursive program, the solution to the base case is actually provided, and what you are going to do, you are going to break this bigger problem into smaller problems. So you go with a simple maybe a C programming event int fact of int n. Okay, and then there is a wrong base case. It may actually cause a stack overflow. If n equal to 100, then return 1, else return n multiplied by fact of n minus 1. So actually in this problem, what you do is this base case for n less than or equal to 1 is actually defined. Okay, and the large value of the number can be solved by converting to smaller one till actually you reach the base case. Okay, so this is how you do with the case of recursion. Okay, and there is a difference between a direct as well as indirect recursion. So a function, generally you call it as fun, is called to be direct recursive if it calls the same function. Okay, and a function is called to be indirect recursive if it calls another function, say fun underscore new. Okay, and this fun underscore new calls a function directly or maybe indirectly. Okay, so this is what you call it to be direct as well as indirect recursion. So direct recursive means if it calls the same function. Indirect recursive means if it calls another function, maybe fun underscore new, and fun underscore new maybe calls either directly or maybe indirectly. So this is an example of direct recursion. So void direct recursive function. Okay, there is some code. Okay, so you have direct recursive function, direct rec function. Okay, and there is some code. Okay, with the case of indirect recursion, so same way you write void indirect recursive function 1. Okay, there is some code. Indirect rec recursive function 2, there is some code. Okay, and finally you go for void indirect recursive function 2. Then you have like some code indirect recursive function 1. Okay, so it's going to call indirect recursive function 1, and then it's going to end the brace. Similarly, you understand the difference between a tailed as well as non-tailed recursion. So a recursive function is called to be tailed recursive when a recursive call is the last particular thing that is going to be executed by the function. Okay, so this is tailed recursive. Tail means what you call it to be end. Okay, so tail, it's definitely present at the end. So when the recursive call is the last thing which is going to be executed by the function. And for this case, normally a question arises about how memory is being allocated to different function calls in recursion. So when any function is called from the main memory, the memory is allocated onto the stack. A recursive function calls itself, and the memory for a call function is allocated on top of the memory allocated to the calling function, and definitely a different copy of the local variables is created for each function call. Okay, so in this case, when the base case is being reached, the function is going to return its value to the function by whom it is called, and the memory is deallocated, and definitely the process will continue. Okay, so definitely a memory is going to be allocated, and whenever the recursive function is going to call itself, the memory for a call function is allocated on the top of the memory allocated to the calling function, and a different copy of the local variables is created for each function call. Okay, so this value is being allocated, and definitely after utilizing all of its functions, the memory is being reallocated, and definitely the process goes on and on. So this is how the memory is allocated to different function calls in recursion. So allocation and deallocation process continues. So this is a C++ program to demonstrate the working of a recursion technique. Okay. So here you have a C++ program to demonstrate working of recursion. So hash include bits/std c++.h. Okay, and then this is actually a C++ program. So using namespace std function, void print function int of test, and if test is less than 1, return, and else cout test. Okay, so you go for the print function test -1. Okay, and then cout test, you are going to return it. You are going to end the brace, and then you have a driver code int main function int test equal to 3. Okay, and then you have print function of test, and when you are going to execute this particular code, okay, you are going to execute this particular code, for everything you go with test -1. So afterwards 3 2 1. Okay, so 3 and then -1 2, then -1 1. Okay, so you are going to start with 3 2 1, and afterwards it's going to increment 1 2 3. Okay, so as long as it is less than 1, it is going to do that 3, and then -1 means 2, 2 -1 means 1. So as long as it is less than 1, it is going to do that, and after that it's going to increment 1 2 and 3. So this is actually demonstrating the working of recursion using C++. So when the print function 3 is being called from the main memory, so memory is going to be allocated to the print function 3, and a local variable test is initialized to 3, and statement 1 to 4 are pushed onto the stack. So what is going to do? It is going to first print 3, and in statement 2 we are going to have print function 2 which is being called, and the memory is allocated to print function 2, and a local variable test is initialized to 2, and statement 1 to 4 is actually pushed into the stack. Okay, so similarly print function 2 calls print function 1, and print function 1 calls print function 0. Okay, so this is how the process takes place, recursion takes place. Here the print function 0 goes to the if statement, and it is going to return to print function 1, and similarly all the remaining statements of print function 1 are being executed, and it is going to return to print function 2, and so on. So generally we will have in the output, so 3 minus 1 it is going to be 2. Okay, and then minus 1 it is going to be 1. Okay, and afterwards when the condition 1 is being reached, then it is going to print from 1 to 3. So this is the memory stack that I'm going to show. So here in the memory stack, you will have void print function 3. So you have test equal to 3, print f modulus d, it's test. Okay, print function 2, and then print f, it is I is modulus d, which is I, and then return. Okay, then you have print function 3 which is going to call print function 2. So this is going to call print function 2, void print function 2 test equal to 2, print f I is modulus d, you are going to print I, print function 1, and then print f I is modulus d, it's I, return. So this print function 2 is going to call print function 1, void print function 1, and then test equal to 1, print f I is modulus d, I. Okay, so print function 0, print f I is modulus d, I, and then it is going to return. So this one is going to call print function 0, void print function 0, test equal to 0, if I is less than 1, and then return. Okay, so this one it is going to return to print function 1, this one is going to return to print function 2, this one is going to return to print function 3. So this is how the memory stack procedure, where each of the print functions is going to call, and then it is going to return the corresponding respective print functions. So we have a program as well as recurrence relation to find the Fibonacci series of n where n is greater than 2. So we have a mathematical equation n, if n is equal to 0, so it's going to compare. Okay, so if n equal to 0 and n equal to 1, so Fibonacci of n equal to fib of n minus 1 plus fib of n minus 2. Otherwise there is a recurrence relation t of n equal to t of n minus 1 plus t of n minus 2 plus order of 1. Okay, so recursive program you have input n equal to 5. Okay, so Fibonacci series is 0 1, 0 plus 1 is 1. Okay, 1 plus 1 is 2, 1 plus 2 is 3. Okay, so this is a C++ code to implement Fibonacci series. So you have hash include bits slash std c++.h using namespace std function, and then this is the function for Fibonacci. Okay, so in fib of int n. Okay, so you have if n equal to 0, return 0, and then if n equal to 1 or n equal to 2, you are going to return 1, and then here you have a recursion function, else return fib of n minus 1 plus fib of n minus 2. Okay, and then you are going to close the brace. So here with the case of the driver code, int main function initialize variable n, so int n equal to 5. So see out Fibonacci series of 5 numbers is, so you have a for loop, int I equal to 0, I less than n, I plus plus. Okay, so as long as it is less than n, it is going to print the value of I and it is going to increment it. So see out fib of I and it is going to return 0. So Fibonacci series of 5 numbers, so 5 numbers 0 and then 1. The next one, 0 plus 1 is 1, 1 plus 1 is actually 2, 1 plus 2 is 3. As long as it is less than 5, it is going to print it, and afterwards the loop terminates. So I hope you would have understood much more about Fibonacci series for n less than 2. And then we discuss about a recursive tree. Okay, so this is actually a recursive tree for input 5, which is going to show a clear picture of how a big problem can be solved into smaller steps. So Fibonacci of n is actually a Fibonacci function where the time complexity depends on the function call. So you have Fibonacci of n equal to, we will have for the best case t of n equal to theta of 2 power n divided by 2. So Fibonacci of 5 is divided by Fibonacci of 4, of Fibonacci of 3, Fibonacci of 4 once again, Fibonacci of 2, once again Fibonacci of 2, Fibonacci of 1 and Fibonacci of 0. Similarly fib of 4, it is subdivided into fib of 3, fib of 3 into fib of 2 and fib of 1, and fib of 2 into fib of 1 and fib of 0. Similarly this fib of 2 divided into fib of 1 and fib of 0, fib of 3 it's going to divide into fib of 2 and fib of 1. So this is how the recursive tree, it's being divided into smaller subtasks. So this is a program and recurrence relation to find the factorial of n for n greater than 2. So this is a mathematical equation 1 if n equal to 0 or n equal to 1. I think the condition remains the same. Okay, so f of n equal to n multiplied by f of n minus 1 for n greater than 1. So we are going to compute the recurrence relation t of n equal to 1 for n equal to 0 and t of n equal to 1 plus t of n minus 1 for n greater than 0. Okay, so this is the case for general condition for n greater than 0 and t of n equal to 1 for n equal to 0. So we are going to go for a recursive program where we have the input as n equal to 5. So factorial of 5 is equal to 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. Okay, so it is 20 multiplied by 3 60, 60 multiplied by 2 120. So this is how you find the factorial of 5. So similar case we are going to go for a C++ code. So this is for implementing a factorial. So hash include bits slash std c++.h. So using namespace std function where we have a factorial function in f of int n. So if n equal to 0 or n equal to 1, it's going to return as 1, and you have a recursive condition else return n equal to f of n minus 1. Then you have a driver code in main function int n equal to 5. So see out factorial of n is actually the function of n. Okay, so you are going to return 0. So So whenever you have the output, when you execute this particular code, you will have factorial of n. That's actually 5. You are initializing n equal to 5 is 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. Okay, so only this thing it's going to return it as 120. Here you have a factorial recursion. So this is actually a diagrammatic representation of what we are going to see. So for user input 5, we are going to have the factorial recursion function. So n multiplied by f of n minus 1. So 5 multiplied by f of 4. This is actually, f of 4 is actually 24. Okay, this is actually 4 multiplied by 3 multiplied by 2. Okay, so 4 multiplied by f of 3. So 4 multiplied by 6. Okay, it's at 24. So this 3 multiplied by f of 2. F of 2 is actually 2. And this is actually 2 multiplied by f of 1. Okay. So 2 multiplied by 1, it's actually 2. So this is how you divide a bigger problem into smaller subtasks. Okay. So we are going to continue with the advantages and disadvantages of recursive programming over iterative programming. So first of all, we will discuss about the
Switch on your voice.
Internship grade type projects,
the disadvantages
practical
of
work
recursive
experience in
programming
software
over
development,
iterative programming would be that
and grow your
both the
developer
recursive as well
portfolio
as the
to
iterative
open new
programs
career
have the
opportunities.
same problem solving process.
Don't copy paste your career in 2021. Learn by building real projects at Cryo and grow your career the right way.
And the recursive program has a greater space requirements than the iterative program.
Teacher,
Because all the
teacher.
functions will remain in the stack until the base case is completed. So definitely,
Teacher.
it is going to consume more time. So which means it has greater time requirements because of the function calls, and it's going to return the overhead. And similarly, if you take in the case of the advantages, the recursion provides a clean and a very simple way to write the code. And for example, some problems like TARF, Hanoi, or maybe tree traversals, it is referred to write the recursive code. So generally, recursive code is being preferred over the iterative code. So we can write such codes also iteratively with the help of a stack data structure. So here are the advantages and disadvantages of the recursive programming over iterative programming. So this is a stack data structure, which is a linear data structure, which is going to follow a particular order in which the operations are performed. So the order can be last in first out or maybe first in last out. Okay. So this is a stack where the insertion and the deletion is going to happen on the same end. Okay. But in the case of this last in first out, we have the push operation, and then you are going to delete it by using the pop operation. So there are many real-time examples of stack. We consider an example of plate stacked over one another in the canteen. So the plate which is at the top is the first one to be removed. Okay. So the plate which is placed at the bottom remains on the stack for the longest period of time. So you cannot remove the last plate at the first. Okay. So it will be seen to follow last in first out or maybe first in last out order. So generally we have three basic operations. We have push, we have pop, or peak or top, and then is empty. With the case of push, it is going to add an item in the stack, and if this stack is being said to be full, which means that you have an overflow condition. Pop means it is going to delete, it is going to remove an item from the stack, and items are popped in the reverse order in which they are pushed. So first item which is at the bottom is the last item to be taken out. And if the stack is empty, which means that it is said to be in underflow condition. And then we have peak or top. We are going to have a return the top element of the stack. So we have is empty, which is going to return true if the stack is empty, else you have a false condition. So how to understand a stack practically? As I told you, the plate of which is kept in a canteen. Okay, so the plate which is at the top is the first one to be removed. So which means that the plate which is placed in the bottommost position remains on the stack for the longest period of time. Okay, so what we have to be push, pop, is empty, and then peak. So here are the most promising applications of stack. So balancing of symbols is one such application. and then infix to postfix or maybe infix to prefix conversion is an application of stack, and then undo feature, redo feature in Photoshop or maybe editor, that's also an application of stack. And then forward feature as well as backward feature in web browsers. For example, if you are going forward by another page and then we are going back, that's also an application of stack. And maybe in some problems, common problems like tar of Hanoi or maybe tree traversals or maybe stock span problem or maybe histogram problem, we tend to apply stack. And then there's one greater application of stack which you call it to be backtracking. So that's a algorithm design technique. So you have an example to be a knight tour problem. We have a n queen problem, and what we are going to do, we are going to find a way through a maze, maybe just like a game like maybe chess or maybe checkers. We are going to dive into some way. If that way is not efficient, then definitely we go to a previous state. Okay, for example, if we consider a game of chess, for example, if we move forward, for example, if the opponent is trying to attack us, then what we do, we go sideways or maybe we come back. So this is an application of stack. And to get back from the current state, we need to store the previous state. For that purpose, we have to require a stack. And in graph algorithms like topological sorting or maybe strongly connected components and memory management, definitely any modern computer uses a stack as a primary management for a running purpose. And each program that is running in the computer system has its own memory allocation. And that's the reason in the application of stack we have string reversal, okay, where one by one each character gets inserted into the stack. So the first character is on the bottom of the stack and the last element is on the top of the stack, okay, just like a plates in a canteen. Okay, so after performing the pop operation on the stack, we get a string in the reverse order. For example, if we remove the
Switch on your
plate 1 by
voice,
1,
teacher.
it's going to reduce and we are going to move to the bottom plate. Okay, so there are two ways to implement a stack, using array or maybe using linked list. Okay, so this is how you're going to apply a stack. So what you are going to do, you are going to write a C++ program to implement the basic stack. Okay, basic stack operation. So hash include bits slash std c++.h. So using namespace std function, define max 1000. So you have class stack int top. So you are going to define the top and then public case int a of max. So which is actually the maximum size of the stack. Okay, and then you have stack function top equal to -1. Okay, and then you define the push operation, which is boolean push int x and then int pop. Okay, and then int peak. Okay, and then boolean is empty. Okay, finally you are going to close it. Boolean stack function, it is push int x. So this if top is greater than equal to max -1, you are going to print the stack overflow. Okay, then you are going to return false. Else case, you are going to go with a of plus plus. You are going to pre-increment the top, which is equal to x. So you are going to print the pushed into the stack and then you are going to return true. And you are going to close the brace and you are going to go with the stack pop operation. Okay, so here if top is less than 0, so see out, you are going to print the stack underflow, return 0. So as long as it is less than 0, it is stack underflow. Else case, int x is equal to a of top minus minus, so return x. So int stack the peak function. So if top is less than 0, it is empty, return 0. Else case, int x is equal to a of top, you are going to return x. Finally, boolean stack is empty. So you are going to exhibit this is empty, return top less than 0. Okay, and then finally you end up with the driver code, okay, to test the above function. Int main function class stack is s.push of 10, s.push of 20, s.push of 30. And then you are going to print the s.pop. It is pop from the stack and it is going to print the all the elements in the stack. So see out elements present in the stack. Okay, and then while not s dot is empty, okay, you are going to print the top element in the stack. Okay, so see out s dot peak function. And then after printing the top element in the stack, you are going to remove the top element in the stack. So s dot pop. After this s dot peak, you are going to go with s dot pop and then you are going to go with return 0. Okay, so this actually, when you execute this particular code, first of all 10 is pushed into the stack, and then 20, and then 30, and then afterwards this 30 is popped from the stack. Okay, so after this 30 is being removed, which means that only element, the top element which remains is 20. Okay, so the element present in the stack is actually 20 and 10 because 30 is removed, so we have 20 and. So here we are going to go for a queue data structure. Okay, so generally a queue is actually a linear structure which is going to follow generally a particular order. Okay, but in queue we don't have first in last out or last in first out. We have only first in first out. Okay, which means that insertion and deletion happen on different ends. Okay, we have in queue operation and then we have dequeue operation. Okay, we have what you call it to be in the first case we have the rear end, and then here we have the front end. Okay, right. So this is how the queue takes place. So we have maybe a queue of consumers for a resource where the consumer who came first is being served first. Maybe let us take in the case of a hotel. Okay, so the family or maybe the person who comes first will be served first. Okay, and the difference between the stack and queue is in removing. Okay, so in a stack we remove the item most recently added, but queue we remove the item the least recently added. Okay, so this is actually first in first out. So this is the application of queue data structure. Queue is used when things don't have to be processed immediately but has to be processed in the first in first out order. Okay, so we have some scenarios, some real-time scenarios. When a resource is shared among multiple consumers, for example like CPU scheduling or maybe disk scheduling, maybe we tend to apply queue. And when data is transferred asynchronously, okay, which means the data not necessarily received at the same rate as being sent between two processes, and the examples include input output buffers, pipes, file input output, and so on. And then with the case of operating systems as well, we have semaphores. Okay, and then we have first come first serve scheduling, we have first in first out queue as well, and then spooling in printers, and then buffer for devices like keyboard. So these are some real-time examples, real-time applications of queue data structures. Even with the case of networks, we have queues in routers or switches, and then we have mail queues as well, and then we have DQ, priority queue, doubly ended priority queue as well. So first of all, we discuss about the priority queue. That's a very important part of queue, which is an abstract data type, and it is similar to the queue. But in priority queue, every element will be having some priority, some top order priority, some least priority as well. And the priority of the elements in a priority queue determines the order in which the elements are removed from the priority queue, and therefore all elements are either arranged maybe in the ascending order or maybe in the descending order. So a priority queue is an extension of the queue with some properties as well. Okay, so every item has a priority. Either it will be having top priority or maybe it will have a least priority. And the element which has the highest priority is dequeued before an element with a lower priority. And if two elements have the same priority, means they would be served according to the order in the queue. Okay, maybe if one is having top order and another one is having least order, so the top order will be served first. So typical priority queue will be having following operation. We will have insertion, where a new element is inserted in the priority queue. It moves to the empty slot from top to bottom or maybe left to right. However, if the element is not in the correct place, means it will be compared with the parent node. And if the element is not in the correct order, means so the elements are swapped. So swapping process continues until all the elements are placed in the correct position. So this is insertion. And then you have deletion. So in a maximum heap, the maximum element is the root node, and it will remove the element which has the maximum priority. So if you remove the root node from the queue, okay, generally this removal would be creating an empty slot which will be further filled with a new insertion. So it is going to compare the newly inserted element with the elements inside the queue to maintain the heap invariant. So this you call it to be deletion. Okay. So it is going to remove the element which has the maximum priority first. And then you have a peak operation. So it's going to return the maximum element from the maximum heap, or maybe minimum element from the minimum heap, without actually deleting the node from the priority queue. So you have a ascending order. Okay. So in the ascending order, you have the priority queue, which is the element with a lower priority queue is given a higher priority in the priority list. Okay. For example, if we have the following elements in a priority queue arranged in an ascending order like 4, 6, 8, 9, 10. Here actually 4 is the smallest number. So 4, since it is the smallest number, it will be given the highest priority in the priority queue. After 4 comes 6, after 6 comes 8, after 8 comes 9, after 9 comes 10. And then descending order, so root node, which is the maximum element in a max heap, so it will remove the element which is having the highest priority. So root node is actually removed from the queue, and this deletion leaves an empty space which will be filled by the fresher insertions in the future. So this heap invariant is maintained by comparing the newly inserted element to all other entries in the queue. So how we are going to implement this priority queue? So that we would go to discuss now. So priority queue, definitely we will have arrays, as I told you earlier, arrays, linked list, heap data structure, and binary search tree as well. So we are going to discuss each of the things. So priority queue can be implemented using array by using this one, struct item, and then int item, int priority. Okay. So here you will have an enqueue operation where you are going to insert this new data into the queue. Okay. And then you have the dequeue operation, which is going to remove the element with the highest priority. And then we have the peak or top operation, which is going to get the highest priority element in the queue without removing it from the queue. So we would implement this priority queue with the help of a C++ program using arrays. Okay. So hash include bits / std c++.h using namespace std function. Here you will have the structure for the elements in the priority queue. So struct item. So this we had already discussed this one. Struct item, int item, and then int priority. So int value, okay, and then int priority. So here you are going to store the element of the priority queue, item PR of 1 lakh. Okay, and then pointer to the last index, int size equal to -1. So we will have a function to insert a new element into the priority queue. So void enqueue, it is int value int priority. Okay, and then we will have the increase the size function. So size ++. And then you are going to insert the element PR size dot value equal to value, PR size dot priority equal to priority. And then there is a function to check the top element, int peak function, okay, int highest priority equal to int underscore in function. Okay, so you have int in equal to -1, and you are going to check for the element with the highest priority. So you have for int I equal to 0, I less than or equal to size, I ++. Okay, and then if the priority is same, then you are going to choose the element with the highest priority, but you are not going to remove the element, but you are going to choose the element with the highest priority. If highest priority equal to PR of I dot priority and int greater than -1, okay, ampersand PR of int dot value less than PR of I dot value. So highest priority is equal to PR of I dot priority, and you are going to equate this int equal to I. Else if highest priority is less than PR of I dot priority and the highest priority is equal to PR of I dot priority, and you are going to equate this int equal to I. And finally you are going to return the position of the element, return int, and you are going to remove the element with the highest priority. For this you use the dequeue operation, void dequeue. You are going to find the position of the element with the highest priority. So int equal to peak function, and you are going to shift the element one index before from the position of the element which has the highest priority. So you have for int I equal to int I less than size I plus plus, and this PR of I equal to PR of I plus 1. So you are going to equate this one. And finally, you are going to decrease the size of the priority queue by 1. So you are going to post decrement it. So size minus minus. After doing all this one, you are going to go with the driver code in order to test the above functions. You have int main function, which will have a function call to insert the elements. Okay. So you have nq operation 10, 2, nq 14, 4, nq 16, 4, and then nq 12, 3. Okay. So it's going to store the top element at the moment. And you have int equal to peak. C out, it is less than PR of int dot value. Okay. And then you have the dq, the top element. You're going to check for this one, dq operation. Okay. And then you're going to check for the top element, int equal to peak. And then C out, you're going to print the PR of int dot value, and then dq the top element, dq operation, and you're going to check for the top element, int equal to peak function. Finally, you're going to print the C out PR of int dot value and then return 0. So for you're going to start with maybe 16 and then post decremented, okay, 14 and then 12 as well. Right. So this is the queue operations, and I had already posted this independent work in the Google Classroom. Please go through them at your best available time. Please complete them within 1 week.